Assalamu alaikum and good evening, everyone. My name is Nuzhat and I'm delighted to be the moderator for today. Welcome to BEAWorld Students Webinar Session number 9. Our speaker for today is Ragib Nihal Sadab. He is a second-year computer engineering student at Khalifa University in Abu Dhabi, UAE. He completed his O-level and AP examinations with distinction from the International School of Shayfat. This achievement led him to being awarded the UAE Golden Visa. As a continuous process to build his technical expertise, Ragib successfully completed a 7-day intensive AI and cyber winter school, gaining foundational competencies in these fields. He further enhanced his skills by participating in a day-long Introduction to Quantum Computing workshop organized by Khalifa University. Today, he will guide us through an insightful overview of quantum computing, its basics, applications, and global implications. We are also joined by our chief guest, Dr. Mehedy Masud, who is a professor at the College of IT at UAE University. I now hand over the floor to Ragib to begin his presentation.
Thank you very much for having me. Thank you to all the people who was attending this session. I want to start by saying that my goal with this session, with this presentation, is actually to raise awareness regarding quantum computing and not to give a detailed explanation of the subject or the physics behind it, because it can be pretty complicated and that's beyond my expertise. What initially led me to start research on this is basically I saw AI is everywhere on the news, but many people overlook another key player in today's technological world, which is quantum computing. I started looking over the subject as I had no clue what it was initially, and I hope I can share some general and useful insights for those who are not familiar or have never heard of this field before. Okay, so to understand what quantum computing is or what quantum computers are, we have to first start looking at classical computers. And these are the computers that you and I use in our day-to-day lives, such as our laptops, our computers, our iPads, even our phones. These are all classical computers, and they are great at what they do. But I want to ask a question, if any of you have wondered, what languages do what computer machines speak or understand? What do classical computers speak in? For example, if I were to type hi on the keyboard, how would the machine actually understand this? Like if I press H on the keyboard, does the computer just read hi exactly? Well, some of you might say, no, they speak in coding languages like Python, Java, Fortran, C++, or even assembly. But more accurately, computers actually speak in binary, in bits, zeros and ones. That's all computers understand. And 0 represents a low signal or off, and 1 would represent a high signal or on. So when you press H on the keyboard, the computer, what it understands is a series of zeros and ones, which represent the letter H that we speak in. Same with the I, it has a different combination of zeros and ones. And what the machine is basically doing is that it translates the H to a binary system that the machines can interpret. And that's how coding languages were developed. Coding languages, programming languages weren't actually a thing before. Computers were first built and people had to manually use switches and wires and actually manually press each switch either on or off to represent these binary signals, because programming languages weren't invented before. And that's where this meme comes in, but it's not actually accurate because programs came after computers were built, and it was a very tedious process when programs weren't there. programming languages weren't there, because some people even had to resort to writing binary on a piece of paper so that computers could actually understand. And so programming languages were then invented, and translators helped machine understand the programming languages you use today for convenience. Next, we move on to transistors. Transistors are actually the building blocks of modern day computers. And what are they exactly and what's their purpose? So transistors actually control the binary signals, the bits we just saw, the zeros and ones. Transistors actually manipulate them and represent them using electrical signals. And these initially were transistors were quite big comparatively. There were a few inches in size. And this picture you see over here, it's one of the oldest computers, but it's one of the first computers that uses transistors. And it is huge. Even though the computers before were big, the transistor allowed us to use less space, but improve our computational power in these machines. Over time, people managed to make transistors very, very small. And nowadays, transistors have become so small, they're around 2 to 5 nanometers wide. That's the size of just a few atoms. And these are smaller than even your blood cells, your red blood cells. And this allowed billions of transistors to fit inside a very small chips. And that's how we have devices like the mobile phone that you can just carry around in your pocket, and its power is way more than any computer that existed, for example, 50 years ago. This is a graph showing Moore's law, which basically shows the trend in transistors per microprocessor or chip. So as you can see, in 1971, in the early days, not many transistors could actually be fit in a chip because transistors were pretty big before. But Moore's law stated that every 2 years, the number of transistors actually doubled per chip. So now, in our current day, we have billions of transistors that we can fit into a single chip. And that's thanks to transistors being very, very small. And the more transistors you have, the more power a classical computer has, and the faster it is. And this right here, these are supercomputers. These are the most powerful types of classical computers, and they have immense processing power. They can perform trillions or even quadrillions of calculations per second. And they're used for demanding tasks in AI and engineering, such as simulations for weather forecast or drug discovery, and training large language models like ChatGPT that require huge amounts of data. And classical computers are great. We use them for traversing the web, the internet, sending emails, chatting with friends, taking photos, and they are amazing at what they do. But they have limitations, of course. And some of the limitations are that classical computers struggle with complex problems that have too many possibilities to deal with. Like if you have to find optimal routes, optimizing certain stuff that have a lot of factors to consider. They're also extremely slow at factoring large numbers. And why would that be important? Because modern encryption methods like the RSA, they're safe because they use the principle of factoring. And the fact that classical computers can't factor that well makes them very safe. And I'll go over that when I go into quantum computers. And another thing is transistors can only get so small. They cannot Moore's law cannot apply forever. There's actually a physical limit to how small they can get before these transistors start behaving weird. They start exhibiting quantum properties, quantum behavior. This is very common at atomic levels. It's actually present in all levels. Even big objects follow quantum physics, but it's only apparent when you get to those small scales. And this will hinder further progress for classical computers. So we would need alternative methods to continue improving performance. And another key thing is simulating nature. Classical computers simulate nature like molecules, but they only do so using approximations, because nature itself is quantum. Nature itself follows quantum physics. So Classical computers are amazing, but they hit this wall and problems grow too complex. Not because classical computers are slow, but the universe is just big. So scientists thought, what if computers could think differently? And what better way to achieve this than a computer that can harness the laws of quantum physics, which nature itself obeys? And that introduces us to quantum computers. And these quantum computers, in very simple terms, quantum is basically the small units of nature, and these quantum computers use these small units of nature, atoms, electrons, photons, to actually perform those complex stuff. And the father of quantum computing can be attributed to David Deutsch, who built on earlier ideas from Richard Feynman and Paul Benioff. Now, quantum uses such small units of nature, atoms, electrons, photons, and classicals have bits. Quantum computers use qubits, which can have a state of 0 or 1, and the weirdest part is it can have a combination of both, or a superposition of both. And this idea can be really hard to grasp for people, and it's completely normal for that because it is not an easy concept. But I'll try my best to simplify it using analogies. So the key idea here is superposition, where a qubit can exist in multiple states at once. You can take, for example, a coin. A coin, while it's spinning, you can't say whether it's heads or tails while it's spinning. But once it stops spinning, it resorts to either a heads or a tails, or 0 or 1, just like classicals. But while it's spinning, it's either a 0 and 1. And actually in this picture, it looks interesting because you can see kind of like a 0 and a 1 here. Just wanted to share that. But that's a useful analogy to think about superposition. And this helps quantum computers achieve great things. Another idea is entanglement, where two qubits can be linked, changing one affects the other. And then there's interference, and interference can be seen in wave physics, if any of you are aware of that. Quantum systems can cancel wrong answers and amplify correct ones, which I'll be showing you in a bit using an example. At the smallest scale, nature doesn't behave like switches, like the binary 0 or 1. The weird part is it behaves like probabilities, and this has to do with quantum physics, which I can't really get into, but I'll try my best as well to explain that soon. Here we have a quantum computer, and this looks maybe not as some of you might expect. It's more like a chandelier, but this huge structure actually functions like a fridge or a refrigerator. How so? Most of this structure is actually used to keep the qubits inside it cool. And the qubits and the quantum chips can actually be found at the bottom. The rest is just to cool the qubits down. And the cooling conditions require the qubits to be at temperatures so low, around -273 degrees Celsius. This is even colder than outer space. And they need to be isolated. Why? What's the reason for that? Qubits actually, because they are basically physically like electrons or atoms or photons, or sometimes even superconductors, these function stably at very low temperatures. And they cannot function, and they need to be completely isolated, because if they come in contact with the outside world, they can misbehave and stop exhibiting their properties. And that's the reason for those. So now let's get into an example where I'll be showing you how classical computers work, very simply, and how quantum computers would solve the same problem. So let's take a problem that requires us to find or search for the number 2, given some inputs. So if it finds the number 2, it gives an output of 1, signaling found or true. And if 2 is not found, it will give 0. So we're going to use inputs, 2 bits of inputs for qubits and bits. Actually, these numbers over here are in binary. 0, 0 represents the number 0, 0, 1 represents 1. 1, 0 represents 2, not 10, because it's in binary. And 1, 1 actually represents the number 3. We're going to be using these 4 numbers only for this function. And the output is either 1 or 0. So that's exactly how it's represented as well. So let's take an example with classical computers over here. Now, I drew 4 blocks, but that's because classical computers actually process instructions one at a time. So you would first give it, for example, a value of 0, it would give you an output of 0 because it's not 2. Actually, 0, 0, it would give you 0. 0, 1 for 1, it will still give you 0. 1, 0 would actually give you 1 because it is 2. And then finally, 1, 1 would give you 0. Now, with quantum classical, it took 4 steps. Quantum, using the principle superposition, you can actually give it all at once. And I'm simplifying heavily here. There are actually different ways of representing this, but for simplicity, I'm using this. 0, 0 would give 0. This would also give 0. 1, 0 would give 1 because 1, 0 is 2. And 1, 1 would give 0. And you see how superposition allowed quantum systems to explore all these possibilities at once? This is what makes them so powerful. But here's the catch. Remember when I said nature works in probabilities? That's actually the key here. We don't actually see this part of the output. And that's the confusing part. What does probabilities mean? Actually, what quantum systems do is that they assign probabilities to each output. So, for example, it could be 25% for all of them. That's one possibility. And how could you imagine this? Well, this is actually pretty hard to explain, but it just is like that, and it's best to just accept it for now, so I can demonstrate you why, what goes on from here. So like, when you try to actually see what the output gives and try to measure it, since all of them have equal probabilities, if you try to measure it, you would get a random value, kind of random because they're all equally probable. And you could either get a 0 when you measure it. What do I mean by measure? Imagine the spinning coin. Measuring the output basically means you stop the coin, and it would be either heads or tails. Same thing here. Once you measure it, it will either be a 0 or a 1. And that depends on the probabilities. Now, this is not very useful because we can't tell if which input the 0 is coming from or where the 1 is coming from. That's why people built algorithms. And what algorithms are, they're basically a set of instructions to solve a specific problem. So there's a quantum algorithm called Grover's algorithm. And this Grover's algorithm tries to make the output useful for problems that require us to find or search for a specific item. And very simply, Grover's algorithm works like this. If you have, it will basically use the concept of interference, which I showed you, which basically cancels out wrong answers and amplifies correct ones. So at the end, using Grover's, you would have 4 outputs, like usual, but these outputs would give you which input gives the value of 1. So instead of 0 and 1, you will get inputs as the output, which is confusing, but I'll get to it. And using interference, it would actually make the probability of the correct answer being higher than the rest. So for example, we assign 97% to the correct answer while giving lower probability to the others. So at the end, when you measure this output, you're very likely to get the correct answer, which is 1, 0, which is number 2. And the way you would check if this is the correct answer is you put 1, 0 back into a classical computer, and it should give the output of 1. But of course, there's a 3% chance here that you get the wrong answer. And you can also verify this and run the Grover's algorithm again, and then it should give you the correct answer because 97% is a high chance. So that's a very simple example. Now let's look at some applications. One of the things that quantum computers expected to be amazing at is simulating nature. And that's because nature follows quantum rules. Classical computers approximate those rules using huge calculations. And molecules are quantum systems, so approximations can break for complex molecules because some molecules are very complex in nature. And quantum computers are built from the systems that already obey those quantum rules. So classicals don't fully simulate reality, they just approximate it. For example, drug discovery requires simulating nature. But instead of classical computers fully solving those quantum problems, they use simplified models, approximations, and lots of trial and error to actually discover drugs and simulate nature. You could think of it like classicals don't actually simulate every atom perfectly. They just simulate just enough to make progress. For example, when designing airplanes, you don't study how every single molecule in the air behaves. Engineers use engineers use models that approximate that enough to get the job done. But quantum computers could potentially simulate molecules exactly, and that leads to faster drug discovery. You can even discover new medicines because it allows you to explore complex structures that classicals just can't. It leads to fewer failed experiments because it reduces the likelihood of errors. Next is optimization problems. And why classical computers struggle here is because optimization, especially with problems that require a huge number of possibilities, finding a globally optimal solution can be very tough. Imagine huge cities with thousands of cars, trucks, bikes, traffic accidents, emergencies, deliveries, passengers taking taxis, if they can make it to the destination in time, deliveries being made, flights, and all that. Imagine having to account for that and finding the best possible scenario to carry out all those in the most optimal manner. Classicals just struggle at that. And imagine you scale it to hundreds of cities, not just one. That's where quantum computers might actually be helpful because of the principle of superposition. Then you have cyber security. And now this is an issue that even governments are worried about. See, quantum computers could pose nationwide threat. And that's because quantum computers are great at factoring large numbers. Now, why is that concerning? Because modern encryption methods are actually built on large numbers that cannot be broken unless they can be factored. An example is RSA, which I'll get into, but basically quantum computers pose a risk and they could possibly break those encryption methods. And simply, what is encryption? When you send a message, when you want to send a message to your friend, for example, over the internet, and if it's something very sensitive, you usually don't want hackers to see or other people to see that message. You want it to be between you and the person receiving it. If you send a password and it's over the internet to your friend, for example, and it's not encrypted, any hacker could intercept that message and easily see your password. To have secure communication, encryption is put into place. Basically, there's an encryption key you can use to encrypt your message. So even if a hacker manages to get access to it or intercept, it would not make sense to them, as you can see over here. It's a bunch of jumbled up letters and numbers. It's not the original message. Only the recipient can decrypt the message using a key to view the original message. Now that brings us to the RSA algorithm, which was developed by Ron Rivest, Adi Shamir, and Leonard Adleman at MIT in 1977. It's a widely used encryption method. RSA is actually used for secure online communication when you're browsing through websites, sending emails, and even some bank transactions. So it's very serious. You don't want hackers to intercept such communication methods, lines. So let's take this example. How does RSA actually work? Let's say Alice wants to send a message to Bob. And to everyone in RSA encryption, everyone has a public key and a private key. Now, a public key is public to everyone. And Alice, in order to send a message to Bob, she would use Bob's public key to encrypt her message. And it looks like this at the end. And only Bob, using his private key, which is only known to him, can decrypt the message to its original. Now, how are these public keys actually calculated? Now, they're calculated basically by multiplying two numbers, let's say P and Q. And by multiplying them, you get a number N. And the number N is actually public. It comes with the public key, and everyone can see the number N. However, to get someone's private key, you would need to know what P and Q are. And that's the hard part. To get P and Q, you would need to factor N into two numbers. Now, that is the hardest part. Simply speaking, if you have number 33, for example, let's say N is 33, it's very easy to find the two factors that give 33. That would be 3 times 11. And actually, they have to be prime numbers in RSA encryption. So these are the two numbers that give you n. And if someone actually had this as their private and public keys, they would be very easy to hack. But that is just not the case. Reality, RSA uses, what if you had like an n value that's very large, several digits? Now, classical computers would take a long time, but if it's a few digits wide, they can still break it within a few hours. But what if you had a number that is this big? Now, these numbers such numbers are used in RSA methods, and they can have 600 to 900 digits. And these would take classical computers, even the most powerful ones, billions of years to actually crack this number and split it into its prime factors. But Peter Shor developed an algorithm in 1994, a quantum algorithm that turns factoring into a pattern-finding problem. And it uses the principle of quantum interference. And this can break RSA faster than any known classical methods. And very simply, how it works is that if you want to find the factors of n, you would actually only need to know one of these. So if you guess p, for example, all you'd have to do is divide n by p, and then you'd get q, and then you'd have p and q, and you can break any RSA encryption. And how Shor's algorithm works is you basically guess a random number. For example, 33 was the n we found. Let's say we don't know what the factors are. We would guess a random number like 2, and Shor's would actually give you a better guess, such as 3. And that would most likely be a factor of 33, and we would divide it by 3 to get q, which is 11. And that's very simply how Shor's algorithm works. There's obviously many complicated stuff inside, but that's the essence of it. And if someone were to have a quantum computer that is powerful enough to do this algorithm for such large numbers, they would actually break this encryption method. That's why governments have already started urging people to come up with new encryption systems, especially quantum-resistant encryption methods, so that these algorithms can't break them. And there are also concepts like quantum key distribution, which is a way to handle such problems. However, there are limits and challenges to quantum computers. One of the biggest is errors. Qubits are actually extremely sensitive. They basically hate the real world. And small things like heat, vibration, radiation create noise, and this leads to errors and decoherence, which is the loss of their quantum behavior. They might not behave as intended because of these outside factors. Number 2 is scaling them is extremely hard. Actually, scaling is hard because we only have about 1,000 qubits, and we would need more qubits to generate more power. But more qubits doesn't automatically mean more power, because more qubits can create more noise as well, which is kind of like a paradox, and which creates more errors. And basically, to create one reliable qubit, we may need hundreds or even thousands of physical qubits, because the qubits we have are not perfect qubits. They're very error-prone. And they need extreme cooling conditions. To keep qubits stable, we need to prevent heat and other stuff from destroying their quantum behavior. And this can be very expensive. Now, I mentioned Shor's algorithm, right? But actually, today's quantum computers can't actually apply Shor's algorithm and break RSA. The largest numbers we can break with our quantum computers is the number 21, which is basically 7 times 3. Any toddler can do this. You don't need a quantum computer for them. But quantum computers are at an early stage. You would actually need about 4,000 perfect qubits to crack today's RSA algorithms. But those are perfect qubits, mind you. So our encryption methods can't actually, quantum computers can't actually break the encryption methods. But that's not all bad news. There is some good news. In 2012, it was estimated that we would need 1 billion qubits to actually break RSA using Shor's, but we only had around 100 qubits at that time. But nowadays, we have about 1,000 qubits, and because our qubits are getting better, it's estimated that we would need around 20 million qubits to break RSA encryption today, but which is still a pretty big number. But if the trend continues, the requirements might even get smaller. So now, where are we? See, quantum is still in research, and quantum chip and the key players in this quantum race have actually built very promising chips. Take, for example, IBM's Condor. IBM's Condor has the largest number of qubits today, 1,121. And they have consistently been breaking and achieving their quantum hardware goals. Just a few years ago, they only had 100. Now they have 1,000. They plan to go even 100,000 within a few years. You then have Google's Willow, which made a huge breakthrough because it's a quantum chip that reduces errors as it scales up, which is huge. And then we have Microsoft's Majorana 1, which uses topological qubits, which are basically more stable qubits, and has a set path to 1 million qubits. And we'll have to see how that plays out. Quantum computers also have a software side, not just hardware. And that's in the form of programs and algorithms. You see, even classical computers work with quantum computers. They're not separate things. They can work together. Classical computers prepares the problem, controls the quantum hardware. Quantum computer runs the quantum part, and classical computers then interprets the result. There are also algorithms, like I mentioned, Grover's and Shor's. There are also other algorithms like VUQE for chemistry and QAOA for optimization. And actually, we're kind of lacking in the software side because developing algorithms is extremely hard. But people are making newer algorithms over the years, so it's also looking very promising. And actually, you at home can also start experimenting with quantum computers. IBM actually has a library called Qiskit, and it's a Python library, so you can code it using Python, which is very cool. And these tools allow anyone to experiment with real quantum hardware via IBM's cloud. So yes, you at home can give instructions using your classical computer, using your laptop, to physical quantum computers at IBM. So finally, is quantum computer the future? Possibly, but not in the way most people think. You see, many people have expectations like quantum will replace classical computers, like your laptop, your phone, your computers. People will only use quantum devices. But that's actually not true. Quantum and classical computers will work together, just like how I showed before, earlier. They will work together. Quantum won't fully replace them. Everything will be run on quantum machines. That's another expectation. And that's related to what I mentioned before. Quantum and classical computers will work together, but classical computers will still be used for most things because most things just work almost perfectly fine with classical computers. Quantum computers are there to just solve the difficult problems, the complex problems that classical computers can't. So they're built for different purposes. People actually overestimate how much quantum computing will do. People say everyone will have a quantum computer. Truth is, most people won't have a quantum computer because they won't need one. And that's because most of your daily tasks can be done with classical computers. And quantum computers have very narrow use cases. Another thing is all governments and businesses will invest in quantum computing. See, quantum computing is not for all. Many businesses still struggle with the basic issues. And quantum computers are still at an early stage. In reality, even if we do have a fully functioning quantum computer today, it wouldn't be of much use because most businesses are still struggling with basic stuff. And the complex stuff only matters once those basic stuff have been dealt with. And so quantum computers will take several years before it becomes actually useful, just like how classical computers back then took around 50 years to actually have a worldwide impact. Quantum computers will also be the same. And don't expect to have quantum computers available tomorrow. Even if it is, you won't be using it for everything. For example, imagine classical computers as being cars, for example. You would use your car to go to places like the grocery, to go shopping, to the movies in your city. Uh, but quantum computers would be like the planes, for example. To travel countries, you wouldn't use cars. You would use planes because they're much more efficient. But then again, you wouldn't use planes to travel everywhere. You wouldn't use planes to go to the grocery. That would actually be even worse than if you were to use classical computers. So that's why classicals will not disappear. They will run most of it, but quantum computers will silently grow with time and solve the most complex tasks that quantum computers just can't. And quantum computers the future of quantum computing is looking very promising, and it's very optimistic the way we're heading, even though it will take a long time to actually reach a stage where quantum computers become useful. The way IBM, Google, and Microsoft, they're all heading. And it's still in research, but it looks very promising, and it would definitely have a place in our world, especially when simulating nature and stuff like that, which classicals just struggle at. It will definitely prove useful in such fields. And that's all. Thank you for listening. And please ask questions if you have.
Thank you, Ragib, for that engaging and informative presentation. You broke down a complex topic in a way that is accessible and thought-provoking. We will now move on to the Q&A session. If you have any questions, kindly raise your hand and I will call your name.
Okay, I can ask more questions before the audience asks the question. So Ragib, you told that quantum computer is still in research and still not formally fully being used in public. So as per progress of the research, what do you think actually? What is the approximate time to start full functioning of quantum computers?
That's a good question. And actually, there's a joke going around in quantum computing that every year they claim that quantum computing will come in the next 10 years, but it's been 10 years and even more, and quantum computers are still not functioning yet. And it will take time. It could take even more time than people might say. For example, it could take 50 years or even 10 years. We're actually not sure. It depends on how fast these companies actually work. And if you look at IBM's goals, they plan, I think, around 2030 to make around 100,000 qubits, which is going to be promising, but it still probably won't be used in most cases. And I can't really give you a clear-cut answer because there's no guarantee. Anything could happen. Theoretically, quantum computing is achievable, but it's all up to the engineers whether there's going to be a limit to how far you can scale these quantum computers. So there's no definite answer to when exactly, but it will take time eventually, and eventually it will happen, and it will play a big role.
Okay, my second question is that you mentioned in your presentation that quantum computer and the traditional computer will run together or work together. So can you, because here most of the engineers from other discipline, huh? So can you tell if you have still it is confirmed by the researcher that which activity will be done by quantum computers and which activity will be done by traditional computers?
Okay, so classical computers are actually going to do most of the stuff that's already being done. For example, browsing the internet, sending emails and all that stuff, things that classical computers are already good at, they're going to continue doing this. And quantum computers are not going to replace this. Some other examples could include, for example, right now, AI is a big topic. and classical computers are actually pretty good at training AI. So we probably won't see quantum computers delving into those fields for now, because classical computers are still good at that. But where quantum computing could actually play a role is in very complex stuff like simulating nature. That's one of the biggest things quantum computers could actually play a role in, because nature itself, as I said, is quantum. And classical computers cannot model quantum particles like molecules and atoms perfectly. And quantum computers are definitely going to play a role in that. And also other areas like optimization. Optimizing, classical computers are good at optimizing, but not when it comes to, for example, you could say smart cities, for example. Let's say a city that is entirely controlled by computers. There would be way too many factors to consider. And if you want to optimize such systems, you would need quantum computers. So basically, in essence, the most complex stuff that have many different possibilities and that are quantum in nature, those are the works that are actually going to be done by quantum computers. And those problems are actually very narrow. Quantum computers won't be used in as many fields as people think. It's actually going to be a very narrow use case, and only very few people in the world will actually find a good use for such quantum computers. So that's my answer.
Thank you so much. I actually had a question as well. If you're someone who wants to get into the quantum computing field, do you think it's too early since it's still in the research and development phase? Do you think it's a good idea to take quantum computing as a technical elective at university or to minor in it? Do you think is it an ideal time to start now?
Okay, that's actually a very good question. First of all, is it too early to start because it's still in research? I wouldn't say it's too early. I'd say it's about the right time, because this is where most of the research is happening. But I wouldn't recommend actually pursuing quantum computing as a field on its own, because it's still in research and there are more quantum enthusiasts than there are jobs available. So you probably won't be able to make a career out of quantum computing, but it is definitely something promising, and starting early can definitely give you a head start. And I would recommend starting off quantum computing as a side thing rather than a main thing. And whether you should pursue quantum computing as a technical elective, I'd say sure, you can go ahead and start, because it's still in research and it's still going to be in research in the next 10, 20 years, I assume. So it's going to be a slow process. And if you're really interested in this field, I'd say go ahead, and you could possibly find ways to make maybe useful contributions to this field, as it's still in research and many people are still coming up with new ideas. And it's fresh, and it's good to start early when most of the fields nowadays are already pretty old. And it's better to get a head start from now. That's my advice.
Okay, thank you so much. We have a question from Abu Naeem Mohammed.
Assalamu alaikum. I'm from Bangladesh. Can you shortly brief again the difference between encryption and decryption of a classical computer and a quantum computer?
Okay, I'll go back to that slide actually. So in principle, encryption and decryption is the same for classical and almost the same in classical and quantum. They basically, the way encryption works is you have a key to encrypt the message. That means to change the way the original message looks so that unauthorized people cannot read the message in its original form. And there would also be another key that is used to decrypt the message. Now, in classicals, I just showed RSA encryption is one of them, where it takes two numbers, P and Q, multiplies them, gets a value N, and some other calculations to actually generate the keys for encryption. That's for classical. However, quantum encryption, there is one popular one that is quantum key distribution, which I haven't really studied too much on it, but so I can't really give you an answer that might be satisfactory. But in essence, quantum key distribution basically lets two people share a secret key in a way that an outsider or a hacker, if a hacker interferes with it, the laws of quantum would detect this intrusion somehow using qubits, the nature of qubits. So in essence, encryption is the same. The idea is the same. It's just different methods that classicals and quantums use.
Thank you so much.
Yeah, no problem.
We have a question from Mohammed Sarfaraz.
Yes, thank you very much. It was very excellent this presentation. I have one thing to know. All of our great scientists, including Stephen Hawking, they're saying within 30, 40, or maximum 50 years, people will start to make habitat to other planets. So my question is how this quantum computer can help to be a human race will be there, how it can be helped, like a communication or other purpose. This is my question.
Okay. So that's actually a good question, and I haven't really looked into this, but what I assume is quantum computing, like even if we do go to different planets, it's still going to be useful because it would allow us to further progress our research in different planets, I guess. For example, how I said nature itself is quantum. Quantum computers could still be used to model nature in other planets and study deeply how other planets are made in the most fundamental, like the smallest levels, down to the smallest atoms and complex molecules. So it could actually further advance our progress into going into other planets way better than classicals, I assume. So that's my take on this issue.
Okay, I can ask the next question that is it available in the market to purchase by the public?
Right now, quantum computers cannot be purchased by the public because they're still in research, and only the biggest companies, they have access to the quantum computers. And actually, they're very big in size, so I don't think any normal household person can just purchase it. But as I mentioned, IBM actually has a cloud quantum computing service where you at home can indirectly access IBM's quantum computers to the internet and actually program those computers. And those are physical quantum computers, but because it's free access to many people, you would actually have to take turns before your code actually is applied to those quantum computers. So that's the only way to actually, the closest way to actually access those computers.
Quantum computer, one kind of scientist in classical computer is general, like this.
Sorry, the voice wasn't clear.
Quantum computer like is scientist.
Quantum computer like science? I'm not sure I understood the question. Can you repeat, please? Or type it in the chat?
Quantum computer is presenting is like a scientist, they want to be intelligent person.
Oh, are you saying quantum computers will become like a scientist, like it becomes intelligent?
Yes, yes.
Oh no, there's no sign of that. That would actually involve AI. That's more into AI than quantum computers. And so far, quantum computers has basically no chance of. There is a chance, but so within the next few years, quantum computers still won't fully integrate with AI. So that is very unlikely. Classical computers are already good at training those large language models and AI and stuff like that. So there's no need for quantum computers to get into that. But maybe in the future, if AI requires even heavier or more optimal training methods, quantum computers could help AI advance even further. The quantum computers won't itself become a sentient or scientist, but it can speed up AI and large language models and train them just a little bit faster. So that's the goal.
We have another question from Abu Naeem Muhammad.
Nuzhat, you can check the chat box. Probably one or two questions are in the chat box.
Oh, okay. I
Okay,
see.
so we have a question from Shaukat Ali Khan. So he's asking about the supercomputer that NVIDIA developed. Is it a mini version of a quantum computer?
The supercomputer is actually a classical computer. So if NVIDIA is selling a supercomputer, a small version of it, that would be basically a very powerful classical computer, not quite a quantum computer. So yeah, that's what I think.
Yeah, I also mentioned this in my previous session, the Jetson Nano. I think that's what you're talking about. That's actually not a quantum computer. It's basically an example of edge AI. It basically allows you to incorporate AI within the devices that you're making. So you don't need internet connection, you don't need a cloud or anything. So you can put the AI directly on the device that you're making. I hope that answers the question. Okay, seeing that we have no more questions, thank you everyone for engaging in the Q&A session.
Sanjay Kumar raised a question.
Yeah.
Okay.
Thank you very much. I was enjoying the presentation very nicely. My question is, although I am a student of electrical, it works based on qubits and superposition, as said. Just I like to know the two terms again, qubits and superposition, particularly superposition.
Okay, let me actually help you by going back to that slide where I talked about it. So yeah, it's over here. So superposition is, for most people, it's actually pretty complicated to grasp. The idea is simple, but it's just hard to make sense of. Superposition basically allows qubits to exist at multiple states. And the simplest way, I guess, to explain this is just like a coin. I'll go back to that again. When you're spinning a coin, for example, it doesn't resort to either heads or tails, right? So it's not 0 or 1. It's actually a superposition of both. So it's kind of both at the same time. And this superposition allows the quantum computers to explore multiple possibilities at once. I hope that kind of answers it.
Yes, thank you. Understood.
Okay, no problem.
We have a question from Mr. Absar. Mr. Absar, would you like to ask a question? Q&A session. Thank you everyone for engaging in the Q&A session. Now I would like to invite Dr. Mehedy Masud to share a few words.
Thank you. First of all, I thank the organizers, Reza Bhai, for arranging such a nice event. And then thanks, Ragib, for your impressive presentation. It gives us very important information about quantum computing. And thanks, Nuzhat, for your nice moderation. So I just would like to point on two things because we don't have much time. Firstly, I'd like to focus on Engineer Shabaraz Bhai asked a very interesting question, whether we can use quantum computing or some kind of form of it for the outer planet inhabitation. So I'd like to mention just one thing. There's a very interesting theory about quantum physics, which is known as entanglement, which Ragib already mentioned. So entanglement, Einstein called it a spooky operation. So how it works, like, let's say you have a qubit on Earth, and you have a qubit on the moon. And somehow you establish the entanglement, quantum entanglement. So whatever state you make the qubit on the Earth, immediately the qubit on the moon will change immediately. This is known as quantum entanglement, and people can use it, and already some Chinese researcher already used it. It's called quantum teleportation. So we have information here, and we want to teleport this information to moon, for example. If we have enough entanglement qubits, we can send it immediately. Normally, if we send light or a magnetic wave from Earth to moon, it takes about 1.5 seconds, right, or 2 seconds. If we want to send some light from Earth to Mars, for example, it will take about 22 minutes. But if we are able to do this entanglement, quantum entanglement, through this quantum teleportation, we could send this information immediately, just in an instant, instead of waiting for 22 minutes. So still it is in infancy. It is, very early stage, but researchers think that it can be done. Already it is done on Earth using the fiber optic cable. In 2024, some Chinese researchers did it for send the quantum teleportation in 30-kilometer distance. The second thing, the question was about the artificial intelligence with quantum computing. Actually, already going on, and already there are libraries. We call it QML, or quantum machine learning libraries, that people can use, and we have used it. Some of my students used it for their projects, but they are basically using the theoretical simulated environment, but there is interface through this quantum machine learning libraries, through which we can interface into the physical quantum machines, and already they are available, as Ragib mentioned, in IBM. Some universities in Australia, they have this facility with the public. We can use them through this interfacing. So basically, you don't have to learn much of quantum computing. You just have to learn these interfaces, just how to use these APIs, and you just use the quantum in the background. So this is how it can work. So I think that's it for now. And thanks again, everyone, for your attendance and nice presentation, question answer. I think still there are a few questions some guests is asking. Nuzhat, can you take a look, please? Thank you. I'm done.
Thank you so much, Dr. Mehedy, for your insights. Mr. Absar, he has a question. He raised his hand.
I am Aryan Abra Chaudhary, his son. So my question is, I have been observing this course from the beginning. So my question is, how does a quantum computer work, and how does it differ from a classical computer nowadays?
Okay, I'll try to explain that very simply once more. So how does a quantum computer actually differ from a classical computer? Classical computers use bits, zeros and ones, but quantum computers use qubits. And what makes the qubits different from the classical bits is that they have many different properties like superposition, entanglement, and interference. And the special thing about qubits is that they can be both 0 and 1 at the same time. And why this is useful is because nature actually behaves like probabilities in the smallest scales. So if you're solving a problem with classical computers, it will still be able to solve most of the problems using bits, because classical computers, if you give it an input, it will give you a direct output, and it's very clear. But quantum computers, they work very well with probabilities and with superposition, actually, as I showed here. This is a good example of how classical and quantum differ. Basically, if you had a problem, like a searching problem, where you have to search for the number 2, a classical computer would have to find each answer one by one. It will have to perform each instruction one at a time. But quantum computers, they can apply superposition, which means they can take all states at once, and this allows them to basically go over all possibilities in a much shorter time than classical computers. And this makes them faster for certain problems. So that's basically how they differ.
Okay, thank you so much, everyone. That concludes the session for today. Thank you all for joining, and we hope to see you in the future sessions.